because it's already time to go ahead with the next session. My name is Michal Frivaldsky. I am from Slovakia, University of Žilina, and my scope of research is power electronics. It's a pleasure to be a chairman of this conference and this session. So maybe just a brief information. Everybody has a 15 minutes, including a time for discussion. So please check your time during the presentation. And yeah, I would be very, very glad if there will be a discussion from the, let's say, plenum. Okay, so the first presenter is Mr. Dejan Drajic from the Serbia. He already is sharing the presentation. So the topic of his paper is a reliable low-cost air quality monitoring using off-the-shelf sensors and statistical calibration. So Dejan, I am giving you a word and go ahead with your presentation.
Thanks a lot. First of all, I would like to say hello to everyone, and I'm really sorry that there is not a real live session, but okay, this year we will do like this. Next year we will be in Lithuania. So my background is actually the time PhD in telecommunications, and I'm working in one R&D company, Dunavnet from Novi Sad, city of Serbia, and we are IoT oriented. In our portfolio, one of the solutions is this air quality monitoring solution, and it's a team of us who developed this solution, and I was particularly involved in signal processing. So I will here try to explain you how the system works, and then specifically what is contribution regarding this calibration. So first, like introduction, you know that air pollution in the city nowadays is increasing because of cars and other things that are used by man. So in the cities, especially in the winter, it's quite critical. It's quite critical in Balkan area and also in Poland. And we also have some cooperation with Polish people. What is the thing? You have static measurement stations, and on the picture you can see how it in reality looks, and it's usually operated by the public authorities. Of course they are reliable and they are able to accurately measure a wide range of air pollutants, but from the other side they are very large, as you can see, very expensive, and require significant amount of maintenance. And extensive cost of acquiring and operating these stations severely limits the number of installations. For example, in Belgrade, there are 2 million people and there is only 6 stations like this. So it's obviously that you cannot cover the whole city, but only 6 fixed points. We developed with low cost gas sensors our solution. Low cost means that these sensors are available and they are more or less reliable, and the cost is 100 euros is the cost of that sensor. And the device, complete device, depends on configuration, but it's about 2,000, 3,000 euros. And on the previous picture, we saw public measurement station, which cost is 200,000 euros. So ratio is 1 to 100 when we compare to price. But we now have to see how accurate are these sensors. And this solution is complete based end-to-end solution that provides real-time measurements. And of course, you can see the device, and it's like the box for the shoes. So it's maybe 1.5 kilos. So it's very small and it's portable, and it could be located wherever you want. So that's the importance of this solution. What we could measure particles, then the different gas pollutants, and important thing is that we have opportunity to use multiple communication interfaces. So any kind of mobile network, also LoRa, it's new low wide area network, but with devices with small consumption of electricity, and Wi-Fi. So we can cover every needed technology, and we have the most of the pollutants that are of interest. And one of these things is that you also have possibility to calculate common air quality index. It's common measure that is used to report the quality in some city. Here device take measurements on every minute and send on Azure, Microsoft Azure platform, where it's stored. And after that, there is a dashboard to visualize real time and historical measurements. And there is a mobile and web widget application for this. So now to go, when you have idea what is solution, now to see the methodology. Here are briefly listed used sensors, and it's every sensors are really low cost sensors. What was the methodology? So you have two possibilities. One is to go to laboratory. The problem in laboratory is that they still don't have quite good procedure that can claim, okay, with this laboratory you will have your accuracy and availability enough, and it's very expensive. You spend for one pollutant, you can spend 1 or 2 days in laboratory, and it could be 5,000 euros. So if you do that, then your low cost solution will not anymore be low cost. And so the best possible solution is actually to collocate this with public monitoring station, physically to go into this place and put your device. Of course, you need access to this, and the local authority has to provide you this. Fortunately, we have more than 10 years of experience with this, and we have good cooperation with the public authorities, so they allowed us to do these measurements. And these are the only measurements that are generally on the world level that are recommended how to do the measurements. Other good things, we had period of 9 months. And these sensors are quite sensitive to temperature and relative humidity. So we have enough opportunity to see, to collect data from all different periods of time. And our resolution is 1 minute. And public authority, they also had 1 minute, but they provide average values for 1 hour. So we were, in order to compare, we also did averaging. And also in this averaging, it's not only averaging of results, but it's also some post-processing. Because during this 1 hour, there should be some problems with, for example, sensors, then some interference, then some problem with electricity or with communication. So it could happen that there will be bad measurement. So we developed algorithm for removing these bad measurements. When we come to mathematics for calibration, we are using curve fitting using least square method. It method performs fitting based on minimization of the sum of squares of deviations from a straight line. So linear calibration. And by this calibration, we are actually calculate coefficients A and B. And now when we do this calibration for the first 15 days, it's recommended number of days. After that, we apply the coefficients on the measurements, and it is the same coefficients are used through the whole period of measurements. And as a result, how good is our measurements after calibration? There is regression analysis, and R2 is actually value that say how good is calibration. 1, it's perfect correlation, 0, no correlation. And now here is result for CO, carbon monoxide. On the left figure, you can see in the time measurements, x-axis is actually our measurements, and y-axis are actually public monitoring station. And you can see how calibration is done. And for this red curve, these coefficients A and B are true regression are done. And when you compare it in real time, you can see the similarity of our measurements and the similarity of our measurements and public monitoring. As you can see, it's 0.933, which is perfect, almost perfect. Then PM, it's a different pollutant, and some pollutants are based on their nature. It's easier to do measurements, some not, unfortunately, because there could be some cross interference from other gases and influence. And actually, these particles, it's actually small particles, micrometers particles in the air, actually dust. And here you can see how it is possible to do calibration. And you can see that here we have R2 0.716. which is still good enough. And here is the table where we compared for all measurement gases, where we compared what is this R2 coefficient during different periods of time. And what can be seen that in February and the August is the lowest. Why? Because at this time of year, humidity, especially in February, and temperature, especially in August, how they influence our measurements. And you can see how it's changed through different part of the year. But the good thing, and you can see that ozone, it's quite heavy to measure. So with ozone, we have the lowest correlation, but it's still correlation. So here, by this is proved that these sensors could be used. And then with this, we can claim, okay, you have our small solution and accuracy will be like that. Then second thing is, as I mentioned, there could be some peaks in the measurements, and we should eliminate that. What we proposed? We proposed algorithm where first we do averaging of measurements for some desired period of time. And the input parameter is length of observed period. After that, we define what is the value of the peak. I mean, if you have measurements that are 1.1, 1.2, 0.9, and then suddenly 5, it could be a peak. So we can then define value x, and we said, okay, this is candidate to be peak if it's x times higher than average value. And finally, maybe it's not peak because of peak. Maybe it's something abnormal is going on in the air. So we must be sure. And because of that, we said, okay, then we could check, is it single peak or it's a few consecutive measurements are peaks. If it's, for example, this is parameter n, and if we put the b 3, it means that we will tolerate up to 3, that is a peak. And after that, if we not that it's peaked, then it's replaced, and it's replaced with mean value of the previous and next measurements. Here it was campaign 15 days and on 1 minute level, because it's our measurements and we want to eliminate peaks. And here are actually, it was period of sliding window for half an hour. Then the peak is candidate if it has 3 times higher value than average. And finally, number 3, it was number of observed consecutive values. And based on that, we also get measure results. And here you can see by gases, and you can see by part of the year. And obviously, it is seen that exactly in this period of year, when it's extreme temperature or humidity, that we have the most of the peaks. And it also depends. O3, ozone, he has the highest number of peaks because of measurement process. And also this ozone it's very hard for monitoring, because he's something in between. Very often he's going from ozone to NO2 and oppositely. And on the figure left, it can be seen peaks and how they are eliminated. Which peaks we eliminated by this algorithm. And finally, it's calculation of common air quality index. Actually, here it's in order, when you have to present your results to ordinary people, they will not understand what is 1.1, 0.9. And because of that, it's calculated air quality index that categorize all measurements in 5 ranges, from low value, very low, to very high. And it's colored from red to green with different nuances. And based on that, it's possible to compare around Europe and around the world all results. And few gases, actually all the gases that we observed, they are actually used for calculating of common air quality index. And it's first calculated by pollutant. So it's sub-index comparison. And here is a presented comparison with the referent monitoring station. We have 100% percentage of overlapping with referent monitoring station for CO. It's different from other gases. And the worst case, it was for O3 in August, 77%. But total common air quality index is calculated when we take the worst pollutant. He dictates the level of common air quality index. So the 4 could be right, and the fifth one could be bad, and it will be the air quality index. And on this level, you can see that in the worst case, we have 80% overlapping with referent monitoring system. And it's the web portal and how it is presented. So in the web portal, you can go and click on your reference on your station, and you can get in real time and in some history time how is common air quality index monitoring. Conclusions is that the idea was to prove that low-cost electrochemical sensors are able to do complementary measurements to public monitoring station. It will never be so accurate as public monitoring, but you can compare the price and the quality. So collocation method was used. Calibration is done with LSM algorithm. Results obtained for a period of 9 months are compared. Proposed algorithm for peaks detection elimination is developed, and common air quality index is calculated and compared with public monitoring station. And the main conclusion is that with a careful data post-processing, low-cost sensors could be used with high reliability as a complementary network to public monitoring station. Final slide is future work, of course. Future work is development of calibration algorithms that are taking into account impact of the air temperature and humidity on readings. So when we apply algorithms, for sure, we will increase correlation. And also analysis of influence of peaks elimination on correlation coefficient will be done, and common air quality comparisons will be done on 24-hour level, because in this work, we compared on 1 hour level. And other thing is to see how it influenced 24-hour. So as you can see, the main conclusion is that these sensors could be used, but you have to be to take care and to do enough good post-processing to increase the correlation of measurements. And basically, I'm sorry, I had only 15 minutes, so it's story for half an hour. But I hope that I give you idea what we are working. Thanks.
Okay, thank you very much, Dejan. Yes, I think you are on time. We still can ask one question for the discussion. So if there is anybody who would like to ask, please feel free. Okay.
Maybe you're interested in air quality in your area, so we can cooperate.
Yeah, I see that there are some also European projects and European calls for the air pollution monitoring, so the development of the sensors and also the statistical, let's say, informations are very important for us.
Yes, because in this, how we get this know-how? Because we were in a FP7 project, City Sense. It was guided by people from Norway, from Norwegian Institute for Weather, and they teach us how to actually do measurements and how to present results and to do post-processing. And now we improved with further algorithms for post-processing, and that's the idea.
So yeah, so it was under the project. So yes, good work. Fine. So if there are no questions, I would like to thank you, Dejan, and we can proceed with the next presentation. So please stop sharing your screen.
Okay, thanks a lot. Yes.
Bye-bye.
Bye.
Okay, and the second paper will be presented, I suppose, by Mr. Vaclav Kolar from the Technical University of the Ostrava, Czech Republic. And the paper is, I think, in cooperation with the Polish colleagues from Gdańsk University of Technology. The topic is a development of a capacitive voltage divider for high voltage measurement as part of a combined current and voltage sensor. So it is also a topic related to the sensing technology. So I would like to welcome Mr. Kolar, and now you can start sharing your presentation and you have a word.
Yeah. So thank you, Mr. Chairman. Can you hear me?
Yes, it's good.
Yes, okay. And Can you see my screen?
It's perfect.
Yeah, okay. So I am Vaclav Kolar from Technical University of Ostrava, and my presentation is about capacitive voltage divider for high voltage measurement. So our team dealt with development of combined voltage and current sensor for measurement in high voltage power networks. This sensor is dedicated to be placed on overhead power voltage line, and it has a remote wireless data transmission, and it should have autonomous operation. It should operate there for at least 20 years. We hope it will be possible, but it will be hard question. Now we started to test it. Yes, purpose of this device is for diagnostic of high voltage power networks, and also voltage measurement, current measurement, and indicative power measurement. We did this development in cooperation with one electrotechnical company from our city, and important thing is also cost effectiveness of this device. It must be relatively cheap. For current measurement, we use their inductive instrument current transformer, but it's not part of this presentation. For voltage measurement, we use capacitive voltage divider because first it is cheaper than, it's much cheaper than inductive instrument voltage transformer, and also it is lighter and smaller. But from some point of view, it's not so accurate as inductive instrument voltage transformer. So we stated some requirements for accuracy in cooperation with the company. Voltage error should be below 0.5%, current error below 2%, and power error below 5%. From these values, we calculated phase angle error. It must be below 0.6%. There is digital data processing with sampling rate 16 kilosamples per second. And if there is some constant error during measurement, which is always plus or always minus 1%, 2%, is not problem. It can be easily corrected. But if error is changing, it is problem. So stability of the all components is very important. Here you can see schematic diagram of voltage divider, and this is high voltage capacitor which we use for it. There are two high voltage capacitors in series, and here as a low voltage part of the divider, we use ceramic capacitors with dielectric C0G. They are very good capacitors, very stable. There is no problem with them. But these high voltage capacitors are relatively cheap, are very robust, and it is important, but they are not dedicated for measuring applications. So we have to test them and find how they work when temperature is changing or so on. So we made such a testing device. Here are two inductive voltage transformers. Originally, they are measuring voltage transformers from 22 kilovolts to 100 volt, and one of them we use as power source in opposite direction from voltage 50 volts. We increased the voltage to 11 kilovolts, and second one was used as a measuring transformer, as a normal instrument voltage transformer. Because we want to test at least 8 capacitors, so because of time saving, there are 3 capacitors simultaneously. We can test 3 dividers together. So high voltage part of the voltage divider and separately low voltage part of the divider, and high voltage part or low voltage part or both of them can be inserted into constant climate chamber and test their temperature dependency. Core of the measuring apparatus is this analog to digital converter by National Instruments, and there are also some another measuring devices, and we measure also temperature. First, we tested long-term stability while temperature was constant. Temperature was about 25 degrees of centigrade. At the beginning, you can see voltage error or voltage deviation. Yes, of course, it's important. Voltage was 11 kilovolts. So 110 volts is 1% of the overall voltage. So at the beginning, error was 0. And as you can see, during time, there is some deviation which stabilizes after 24 or 48 hours. Some capacitors are more stable, some capacitors are stable less. So important is after assembling the voltage divider, it must be somehow calibrated, but not immediately, but it has to be connected to voltage, and we must do calibration after at least 1 day. 2 days is better. As far as phase error is small. It is within limits which was stated. Phase error is not problem from this point of view. Then we tested temperature stability of capacitive dividers in constant climate chamber. Here you can see changing of temperature from 25 degrees of centigrade to about 70, back to 25, to minus 25, and back to 25. Phase error changed, but not too much. It is still within stated limits, but amplitude error changed a lot. 250 volts, it is more than 2% of measured value, and it is too much. It must be somehow compensated. So in this picture, you can see temperature dependency of each tested capacitor. Low voltage capacitors are okay. There was no problem with them. Phase error, there is phase error, but not very big. But most important is this amplitude error of high voltage capacitors. Fortunately, this is linear function, almost linear function of temperature, so it can be quite easily compensated by such formulas. We decided to correct phase angle error only by constant, which is independent on temperature, and amplitude error by this formula, what is linear function of temperature. According to these equations, we get these coefficients. In this table, you can see values measured when temperature was 0 and temperature was 25, and final correction coefficients. After this, we chose from our 8 capacitors, we chose 3 of them, which was the worst, and tested them again in constant climate chamber, and we used that mathematical equations to correct measured values. So here you can see again how to temperature changed. Here you can see voltage error after mathematical compensation, and here you can see phase error. All of them are now within limits which we stated at the beginning. And here for amplitude error, you can see there are such peaks. Always when temperature changes from one value to another value, there is peaks of error. It is still within limits. Limit is about 55 volts, and it is below 50, so it is okay. But if it would be possible to remove these peaks, the result will be very, very good. I think it is because of temperature time constant of capacitor, because capacitor is big, and when temperature penetrate from outside environment inside the capacitor, it takes some time, and there is some temperature transient. So maybe it is possible to develop some mathematical algorithm which consider temperature time constant of capacitor and which can suppress these peaks. But until now, we didn't test it such algorithm. So with this mathematical compensation, our capacitive divider is good enough to be used in combined current and voltage sensor for high voltage measurement. We finished several pieces of prototypes of such sensors, and now they are tested in testing laboratory of our industrial partner, and we hope in future it will be produced commercially. So thank you for your attention. And do you have any questions?
Okay, Vaclav, thank you for your presentation. So now I am opening the discussion. So are there any questions from the auditorium? Probably there are no questions. I would like to say that this work was very interesting for me, as I understand the requirements on the accuracy, and I very appreciate the experimental approach and testing. So maybe I will ask you, did you also test these sensors also in operation? Let's say some transition line or something like that?
Not yet.
Not yet. Mm-hmm.
We did this testing with lower voltage than is nominal voltage at 11 kilovolts, but there was one capacitor. In reality, there will be 22 kilovolts and 2 capacitors.
Oh, okay.
And our industrial partner has better laboratory. They test it now in 22 kilovolts, but only in, as I know, only in laboratory. It will go to field, but in future.
in future. Yeah, because such a sensors also need some kind of certification and
Of course.
additional testing. So there is a long way still to be done. Okay, thank you very much, Václav. Now you can stop sharing your presentation. And we will continue with the other paper from the colleagues from Turkey. And the presenter will be Mr. Mehmet Demirtas. The topic of this paper is lossy capacitance measurement circuit based on analog lock in detection. So it's some kind of additional informations or very similar problematics to previous presentation. We can compare and discuss maybe. So you are free to start sharing your presentation, Mehmet, and I am giving you a word.
Thank you, Mr. Chairman. Hello, everyone. My name is Mehmet Demirtas. I am from Turkey. I'm a PhD student, and my presentation is about a measurement circuit, which is titled as a lossy capacitance measurement circuit based on analog lock-in detection. Here, the contents of my presentation. First of all, I will start with the introduction part. Then I will talk about the design circuit that will measure the loss capacitance. Then I will move to the theoretical analysis of the design circuit. Then I will analyze that circuit on LT-SPICE and Vivado, that is called as computer-based analysis. And then I will show the experimental results that I carried on before the conclusion part. And first of all, the introduction part. The capacitance measuring is actually an efficient method to detect many real-world parameters. For example, we can use capacitive measurement techniques to detect displacement, pressure, force, humidity, moisture, or something like liquid level measurement. And also, we also know that capacitance can be lossy. I mean, they are inherently lossy, and they can be represented as an ideal capacitance in parallel with a resistance, as it is shown in this picture here. The lossy capacitance model is shown here. There is a resistance and there is a capacitance. They are connected to each other in parallel. And also, there might be some stray capacitances, and they are called as CP1 and CP2. They are actually parasitic capacitances, and they can arise from the connecting the capacitance to a circuit. Therefore, they should be eliminated, actually. Their effects may cause problems in measurements. Therefore, their effects should be reduced by exciting or driving the lossy capacitance with a low impedance input signal. And also, we can virtually ground terminal 2 by using an operational amplifier so that the effects of stray capacitances will be reduced. And this is the overall measurement circuit diagram that we use to measure the lossy capacitance model. Let me talk more about the design circuit here. We used FPGA to generate the sinusoidal excitation signal so that we drive the lossy capacitance model with a sinusoidal signal. And this is generated using FPGA. Also, we need square reference waves, and they are also generated using FPGA. Also, FPGA is also used to measure the output of the analog measurement circuit. In our FPGA, there's an integrated ADC, analog to digital converter, and we use that ADC to measure the output. Also, there is a transimpedance amplifier, and it converts the current which flows through the lossy capacitance model into a voltage value, and that voltage value is actually will be processed and demodulated by the analog lock-in detection. And transimpedance amplifier can be designed using an operational amplifier and a feedback resistor. Using the analog lock-in detector circuit, we can able to extract the values of lossy capacitance model. Here is the theoretical analysis. The voltage at the output of the transimpedance amplifier can be expressed as a function of input voltage and feedback resistor, unknown resistance, unknown capacitance, and the frequency of the input voltage. Therefore, the output of transimpedance amplifier can be expressed as a sinusoidal signal with different amplitude and phase, but with the same frequency as the input. So input is actually modulated by transimpedance amplifier. And the output voltage, if you look at the output expression of the transimpedance amplifier, there are two terms, and they are actually 90 degrees phase shifted version. They are 90 degrees phase shifted. Therefore, we can use the first component in the red circle in order to find the unknown resistance Rx. And the second component can be used to find the unknown capacitance. Also, we can theoretically analyze the lock-in detector. Lock-in detector is a known methodology, and it is widely used in demodulation actually. And if we assume that the input of the lock-in detector is x of t is equal to a times sine omega t plus theta, and also we have two different reference signals. They are used to open and close the switches in the lock-in detector. And they are square waves, and they are shifted version of each other. And they can be expressed as a sum of sinusoidals with different amplitudes and with different frequencies. Therefore, if we multiply the input with the reference signals, then we will get in-phase output and quadrature phase output. They are called respectively I and Q. Actually, I consists of the in-phase output consists of a DC component plus some higher frequency terms. And also, similarly, quadrature phase output also consists of a DC component and some higher frequency terms. And in lock-in detector circuit, there is a low-pass filter which eliminates the higher frequency components, and its cutoff frequency should be lower than omega. And then we can obtain I and Q values such that I is equal to 2 over pi times I cosine theta, and quadrature phase output is 2 over pi I times A times sine of t, theta. And the unknown resistance and capacitance can be extracted using I and Q components plus the output equation of the transimpedance amplifier. And if we combine the equations together, we obtain the Rx and Cx equations here. Therefore, if we are able to measure I and Q components at the output of the lock-in detector, then we are able to find Rx and Cx altogether. If you look at the computer-based analysis, as I told before, we used an FPGA to generate the excitation signal which drives the lossy capacitance. And it is actually a 2 kHz signal with an amplitude of 3.3 peak to peak. And if we need reference signals with the same frequency, but they are shifted version of each other. So we can see the Vivado graph here. They are shifted where there are reference signals and the sine wave altogether. And also we analyzed this circuit in LT Spice, and we used some certain values, some discrete values to simulate or emulate the lossy capacitance. For example, here we have the schematic of the lossy capacitance and transimpedance amplifier. Here is the unknown resistance is 4.7 K and unknown capacitance is 10 nanofarads. And also we used an operational amplifier with a feedback resistance of 10 K. And if you look at the frequency response and transient response of the circuit, we can see that the output of the transimpedance amplifier is amplitude and phase modulated version of the input signals. Also, we can analyze the schematic of the lock-in amplifier together. Lock-in amplifier actually consists of two different parts. The first part is multiplication part, which uses 4 switches, 4 resistors, and an operational amplifier. And low-pass filter part is actually taking the average of the output of the multiplication. So therefore, we can obtain the I and Q values using the average, that average value. For example, in this schematic, we have shown the input and output signals of multiplication. If there is a sinusoidal input to this lock-in amplifier, the output of multiplication will be something similar to full wave rectified version of the input. And the output of low-pass filter will show the average value of the output of multiplication. We can see that it's actually 0.6346 volts of that output of multiplication. The average value is equal to 0.6 volts, around 0.6 volts. Then we assembled together all the circuits in the LT spice and we got the simulation results. For example, here we simulated 3 different lossy capacitances. They are all emulated using discrete elements. For example, the first element is 4.7K and it represents the loss resistance part, and 10 nanofarad represents the pure capacitance part. They are all together represents the lossy capacitance part. And there are 3 different lossy capacitances simulation results. For example, actually the first column on the RX and C, the first 2 columns represents the nominal values of the lossy capacitance parameters. And at the right-hand side, we can see the simulated values of the RX and CX, which are found using the LT spice simulations, using I and Q values. If you look at the computer-based analysis more deeply, we can see that actually we can simulate the relative error, and relative error actually represents the difference between the simulated value and real value. For example, for the relative error for the capacitance measurement is 0.89% for this circuit simulation. And there is also, we defined a case, which we call it worst case error, which is actually used to assess and measure the effect of the tolerances of the passive circuit elements. Because we already know that this is an analog circuit, analog lock-in detector circuit, and there are many passive circuit elements like resistors and capacitors, and they have tolerances. Therefore, we should know their effects, if their tolerances affect our measurement results or our errors. If they cause error, we should be able to know that. And if we simulate the worst case error, there is, for example, for the capacitance measurement, 3.41% error is maximum. And also, there is another error analysis method we call as phase error, which is defined as the error caused by the phase mismatch between the input signal and the reference signals. Because we know that the input signal and the reference signal, they should be synchronized, and there should be no phase mismatch between them. If there is a phase mismatch between them, they may cause errors. For example, there is an intentional 5% phase mismatch is given for the simulation, and the error is really high. There are errors really high. We can see that on the right-hand side. And also, we tried that simulations and we tried to make it experimentally, and we can see the experimental photo of the circuit that designed to measure the lossy capacitance. There is an FPGA chip on the left-hand side, and also that FPGA's ADC is used. Also, signals are generated using an FPGA, and some other analog parts are designed on a breadboard. Here, I explain the experimental setup. The FPGA we used for generated requiring signals is called Xilinx Z-board. And the analog locking detector, as I told, is built on a breadboard. And also, AD844 high-speed op-amps, and 3 of them are used as part of transimpedance amplifier, multiplication unit, and low-pass filter. Also, we used switches, a CD4066B. It is a quad bilateral switch that is used to multiply the input signal with reference signals so the demodulation will be possible. And also, as I told before, Z-board's 12-bit 1 megasample per second ADC is used to measure the output voltage. And also, if we obtain the results, and we can see the experimental results. Also, we compared 2 different values here, because if we measure a real component, a real discrete resistor or capacitor, we should know it is real value before measuring with this circuit. And the real values of the capacitance and resistance are obtained from an LCR meter that can measure resistance and capacitance with 0.5 and 0.7 accuracy. And we compared the real values of Rx and Cx with the measured values of Rx and Cx, and we found out the relative errors. Especially here, the maximum relative error is 1.62% for the resistance measurement and 6.38 for the capacitance measurement. And those errors can be associated, actually, the causes of errors can be, for example, the on resistance of the switch that used to multiply the signals, or, for example, non-ideal characteristics of the operational amplifiers, or maybe the variations of the passive components, their values, of course, they have tolerances and they may cause errors in the experimental setup. Finally, the purpose of this study, as I told, design, simulate, and experimentally test the lossy capacitance. Here, that is a hybrid system which consists of a digital signal platform, which is called FPGA, and analog circuit elements like operational amplifiers and passive elements. And in simulation environment in LT-SPICE, we use three different error analyses to determine the possible sources of errors. Actually, for example, we found out that the tolerances of the passive elements like resistors or capacitors may cause some errors actually. And also another major factor, actually it is bigger factor than the previous one. Another major factor that may cause measurement error is identified as the phase shift. I mean, the phase shift must be controlled accurately, otherwise there will be a big amount of error. Therefore, in order to reduce the effect of phase mismatch, we use the excitation signal and reference signals which are generated from the same FPGA using the same internal global clock, so that their phase shift is accurately controlled in the digital domain. And also, by using an FPGA and using digital ways to control the phase shift, the circuits like analog phase shifter or analog switch driving circuit suggested in the literature, for example, they are no longer required in this circuit type. Also, this circuit, this measurement setup, or let's say, can measure the final DC output of the system I or Q values with precision, with 3-point precision, so that we no longer need a separate measurement device. Thank you for your interest.
Okay, Mehmet, thank you very much for your nice presentation. If there are any questions, we need to speed up, so someone from auditorium. Probably no questions, so we have to little bit speed up. So Mehmet, thank you very much once more.
I thank you.
And we are going to continue with another paper. So the next paper is from the Slovakia, from Department of Mechatronics Electronics, University of Žilina, and it was made in cooperation with the Technical University in Brno. Now I would like to ask Mr. Bajzik to share his presentation. And Jakub, I am giving you a word, so you are in charge now.
Thank you very much. So can you hear me and can you see my presentation?
Everything is okay.
Okay, thank you very much. So let me introduce myself. My name is Jakub Bajzik and I would like to present you results of our work, gunshot detection using convolutional neural networks. So the main motivation and objectives of our research is the design a citable method for classifying sound events using neural networks. In recent years, it has become a topical task to use some techniques, some known techniques to detect environmental sounds that may be associated with the potential dangers such as explosion or gunshot, siren, car alarm, and so on. So this work is focused on the possibility of using audio visualizations as a future for convolutional neural network training for gunshot detection. In our application, the important task is not only the increasing the number of true prediction when the gunshot is predicted as a gunshot, but also reduce the number of false positive predictions because we cannot detect the every impulsive sound such as door opening as a gunshot prediction. The conventional approach is to create a single future vector for classifiers and for training. In our work, the combination of several future matrices to a single color image is used. The main advantage of this approach is that the futures are overlapped in matched time positions. This method was used in previous study for the classification of environmental sound, but the novelty of our paper is in the analysis of this method described and implementation for specific event recognition with respect to the time consumption and precision. The most commonly audio signal visualization used in practice is a spectrogram that shows the frequency spectrum change over time. Another representation uses the Mel frequency capsule coefficients, which reflects the non-linear and masking characteristics of human hearing. The last feature used is the measure of self-similarity of the signal based on the distances. That is similarity metrics. So the two-dimensional matrices as individual color channels, as you can see on the figures, were joined to the resulting image, as you can see on these two images. We assume that the MFCC and similarity metrics will help to classify non-impulsive background sounds. As you can see on this figure, the self-similarity matrix layer of gunshot is almost empty, is black, whereas the background noise contains a visible grid. So in the experiment, we performed several tests. We used a different convolutional models for future extraction. We compare the pre-trained weights against the training wall convolutional model. We also tested the signal downsampling, and we compare our results with commercial approach when the spectrogram visualization is used only. The weights of model VGG16 are pre-trained on the ImageNet database for real-world object recognition. Only the hidden layer was unlocked for training. In the case of ResNet 18, all the layers of convolutional model were unlocked for training. The advantage of this approach is that the training convolutional neural network is more adapted for detecting specific shapes in gunshot visualization. The result shows that the training all convolutional layers of model ResNet 18 leads to the best resulting accuracy. As I pointed, when we train all convolutional layers, the algorithm is more adapted for the specific sound visualization and can extract the features more precisely. Also, the signal downsampling does not lead to significant decrease in the resulting accuracy. That means that if we can detect impulsive sound, that based on our results, the signal downsampling does not decrease the accuracy. The practical application was designed for the testing for testing the algorithm on a long duration recordings. The application processes the audio signal in 1 second length segment with a quarter-second time shift. Based on our previous results, we use the model ResNet 18 and signal downsampling in this application. So the algorithm was tested on audio recordings of urban sounds mixed with gunshots. And these gunshots we obtain by recording in indoor shooting range. We record this gunshot using portable audio recorder. Also, the proposed method we evaluated or tested on audio recording of similar impulsive sounds. As you can see on a figure, this is a slam on a drum, door opening, and this is gunshot. So the result may differ by selecting the threshold and sensitivity parameters. In this case, the threshold parameters means the minimal probability of belonging to a class to be a gunshot, and the sensitivity parameter is the minimal number of consecutive positive prediction. To achieve the same results as in this case, in a noisy environment may be essential to lower the threshold value, which may cause an increase in false positives. The real-time performance optimization was also tested. The algorithm or the future extraction time from a 1 second length segment is about 80 milliseconds, and lowest prediction time was reached by using model ResNet 18. So also the lowest prediction time and also the best accuracy was reached by ResNet 18. And total processing time is about half a second. So the real-time performance is also real. We pointed out these conclusions of our results, and the first is that the convolutional models can be used for audio visualization recognition despite the fact that they are designed mainly for real-world object recognition in images. This may be helpful in situations or in application where we cannot implement the audio recognition and image recognition framework separately, or we want to use the same framework with both. But when we adapt the model for specific audio visualization, we can achieve the better results. In case of impulsive sounds, such as gunshot, the bitrate reduction without significant accuracy decrease can be achieved by signal downsampling. And also, as I pointed out, the maximal accuracy and minimal processing time can be achieved by using model ResNet 18 with train and weight of convolutional layers. So thank you for your attention, and if you have any question, I would like to answer.
Jakub, thank you very much for your presentation. It was once more applied research with a nice experimental verification. So I am opening discussions. So are there any questions from the auditorium? Maybe not. So as I am familiar with this research, because Mr. Jakub Bajzik is my colleague, we can discuss internally. And now we can proceed to the next paper. Jakub, thank you. You can stop sharing your presentation. And now I would like to ask Mr. Alitat from the Turkey, the Technical University of Eskişehir. Okay, we can see your presentation, and fine. The topic is a time series prediction for amount of airworthiness based on time delay neural networks. So now, please, Ali, you are free to start the presentation and check your time.
Thank you. Good morning, ladies and gentlemen. I would like to quickly introduce myself. I am Ali Tatlı from Departments of Avionics, Eskişehir Technical University. I will try to present our study with my fluent English. This is a piloting study that we are supported with instructor pilots. A significant study before us isn't included in the literature about airworthiness. They are not many, and they are not detailed. And also, they do not meet some requirements. This is a signal processing with unique problem. Because of the time is limited, I want to summarize our study. We have some criterions to create a airworthiness dataset from meta reports with the contribution of pilots. This is the important part of this study, I think. And then we built different type of neural network models to make predictions on it. Neural networks are well known in the literature. We experienced in our study 10 type of input datasets, 4 type of activation functions, and from 3 to 60 number of hidden layer neuron. To begin, I would like to introduce to you my presentation plan. My talk is divided into 6 main sections. First, I am going to present the importance of study. In the next section, I will give information where the study is conducted. It is important because of runway. And then which meteorological dataset we have used to form airworthiness dataset. The next thing I will share with you is what is principal components of airworthiness and how we create the airworthiness dataset to make our predictions. Then I will introduce our methods about predictions. Finally, I will ask you to results. First of all, we need to focus on these headlines to make understand easily. And I think this is important because of the method we have used in the study. I mean, time delay neural network has been known for years. There are legal restrictions in aeronautical information publication, AIP, which you have to comply. You cannot fly whenever you want in aviation. Pilot experience, which you have to consider. Instructor pilots assist the study with the limits that they use in education activities. Our study covers flight training organizations, not for all of the aviation society. And there are some technical issues, differs from aircraft to aircraft. In this this is a meteorology-oriented study. Meteorological parameters and events directly affect flight activities. And also, from another perspective, meteorology knowledge makes it possible for aviation activities to be carried out. From first perspective, aviation activities are mostly carried out in the troposphere and stratosphere layers of the atmosphere, and aviation activities exposed to weather events in the troposphere, where meteorological events occur. Flight training organizations prefer to keep simple aircraft in their inventory because of maintenance and equipment costs. Although these aircraft are more vulnerable to meteorological events. Approximately 20% of the accidents that take place in the aviation sector are meteorological origin. And when considering in the inexperienced pilot candidates, it is so important for the training process. From other perspective, the flight and maintenance schedules, the travel times, the movement routes, and the flight altitudes are determined in the light of meteorological information. Provision of times that aren't suitable for flight is also an important factor in the planning of maintenance activities. To sum up, simple aircraft and inexperienced pilot candidates require meteorological parameters to be well analyzed and predicted. Planning can be made more effective by separating the days that aren't suitable for the flight to maintenance activities. According to International Civil Aviation Organization, it is considered necessary that taken into account a period of at least 5 years in meteorology-focused aviation surveys conducted in Annex 3. In this study, a time series including hourly flight availability per day information was created by using hourly metal and specie observations belonging to Hasan Polatkan Airport, covering the period of from January 2009 to June 2015. It means there are 58,053 hourly meta and specie reports we have used. Here an example of a report and its meaning. We decode reports and use it in the study. It has many information about weather conditions. For example, wind speed and direction, cloud sailing and covering, prevailing visibility. Let's take a look at LTBY station. This is a satellite image from our avionics department of university and LTBY airport. LTBY station is used by Department of Flight Training to carry out education activities. General information about the airport is given in table. All of the properties most important to us is runway direction. Because of aircraft must take position relative to the heading of runway during their landing and takeoff. For this reason, crosswind components exceeding the limits according to the type of the aircraft restrict the use of the runway for the relevant aircraft. The direction of the runway doesn't change, but the direction of the wind often changes. Other parameters are indirectly affect airworthiness. These are Cessna and TB-20 aircrafts in the inventory of university. Depending on the intended uses, the design and flight performance of aircrafts are different, so they are affected from meteorological events at different levels. Besides, as a technical criterion, wind speed and gust condition according to the runway heading shouldn't exceed the crosswind limits of the training aircraft. It is 15 knots for Cessna and 25 knots for TB-20 aircrafts. The majority of the education-oriented aviation activities are completed under visual flight rules. As stated in the Turkish Aeronautical Information Publication, AIP, the VFR visual flight rules, the VFR flights cannot be made in the process, which covers the cloud sailing falls below 1,500 feet, the visibility falls below 5 kilometers, and also 20 minutes after sunset and 20 minutes before sunrise. We calculate sunrise and sunset times for all the time periods 6.5 years that we research in terms of night conditions. And we checked with these three criterion all of the meta reports if it is valid with regard to VFR or not. But this is not enough. In this study, both the VFR conditions and the absence of aerodrome announcement and significant meteorological event that will affect aviation operations are evaluated as a measure of airworthiness. Utilizing plot experience, the conditions are considered necessary for airworthiness. There should be no heavy torrential rainfall, thunderstorms, clouds of cumulonimbus and cumulus congentus. Cloud cover should be less than 5 of the 8 octa. Cloud sailing should be more than 3,000 meters, and also temperature should be more than 5 degrees. We created our airworthiness data in the light of all these limits. Artificial neural networks constitute a model that will generate suitable outputs in response to the network inputs. Determining the appropriate network weights of this model is called the training process. I mean, training is an error minimization process between input and output. Also, when inputs are time series, the use of time information can provide meaningful information to the network in establishing the input and output relationship. The time information can be provided directly to the network as an input, as a numerical quantity, or it may be provided in the form of a time window. So, network could be available to recognize the patterns that evolve over time. I mean, a time information to the network may be provided by the changing frequency of an input signal. By incorporating time into the operation of the artificial neural network, it can be possible that statistical variations can be followed in a non-stationary time series. In the study, we provide the time information into the network both as a direct input to the network and as a part of the network's operation. Also, in our experiment, we use some activation functions. We change and train it. The network structures consist of 4 models with no lag, 1 time lag, 2 times, and 3 times lag delay. Thus, by using 10 data sets as input, a total of 9,280 network models have been trained and tested. The best is underlined. The comparison best result of conventional MLP at the top and the time delay neural network at the bottom. Thank you for your attention. Is there any question?
Ali, thank you for being in time, so I'm opening discussion. So if there are no questions, we will continue due to the time schedule. Ali, thank you very much for your nice presentation and very interesting topic.
Thank you.
You can stop sharing the screen, okay. And now I would like to ask Mr. Pančík from the University of Žilina to present his contribution, which is focused on the electronics upgrade of cyclic loading test machines for automotive production. Juraj, you can start sharing your screen, and now you are in charge. So go ahead with the presentation. Juraj, you have to unmute your microphone.
Thank you very much,
Okay.
Mr. Chairman. Hello, everybody. I'm last today. I will be quick. So let me say a few words about our project. Please, can you see my presentation?
It's okay.
Yes, thank you very much, Mr. Chairman. In our contribution, we describe the upgrade of 8 of the machines designed for cyclic testing of automotion mechanical safety critical components in the real production plant. Tested mechanical components were hydraulic brakes were classified as safety critical, and there were one part of complex hydraulic component. At first glance, it might seem purely technical problem and does not need to address the broader context of common upgrading test machines. From the point of view of functional safety in the automotion, according to the standard ISO 26262, it was necessary to meet the specific requirements in the modernization of the testing machines. Designed and realized information system as temporary solution was cost-effective solution for 4 years, and it prepared the purchasing a new final testing solution in the production plant. The present modernization solution is also a good example of the cooperation of the university and the production plant. The matter of fatigue testing of hydraulic brake calipers is performing of many mechanical cycles where brake calipers squeeze the brake pads against the surface of the disc brake pads in disc. You can see this picture. Existing electromechanical counters of mechanical test cycles which are integrated in the all test machines serve as a source of input data for test engineers. Test engineer can read of a number of performed mechanical cycles, by manual reading from electromechanical counter. After all upgrading of brake test machines, the test engineer can also read of a number of mechanical cycles via by us developed electronic modules. The end of particular test of tested mechanical part is determined by automatic stop of test machine cycling when the part is suddenly broken. Test engineers should be informed about this test machine stop state in the shortest time by us developed information system. By upgrading of collection of 8 test machines, we reached of automatic collection of cycling data. The number of performed mechanical cycles during the particular test for each particular mechanical parts are collected in the database. All upgraded test systems served for testing of caliper integrated EPB, electronic parking brake, or caliper integrated EPB. The EPB system consists of the actuators that generate the clamp force necessary to safe hold the vehicle, the conventional calipers that convert the clamp force into brake torque, electronic hardware with the electronic control unit, and cable harness and switches, especially the control software providing the functions that the driver will experience. The figure shows a typical EPB actuator and caliper assembly. The actuator is screwed on the brake caliper. This is actuator. The spindle gear sets converts the rotational torque coming from motor. Belt drive and planetary gear, this one, set into transversal clamp force that is applied to the conventional piston. This piston is here. A brake fluid is present in the piston chamber and separated from the sealed actuator. This figure gives us some examples with typical functions of actual EPB systems. The apply release process for EPB system represents its main functionality. Since the EPB was first launched in the 2001 year, number of EPB functions continues to rise significantly. Modern EPB offers by far more than the basic apply release of a conventional parking brake, and it interacts with several other driver assistance systems. You can see remote control parking, start-stop assist, hill assist, K-out apply, dray away assist, emergency braking. There are a lot of functions, about 30 functions implemented in the SC module, and modern EPB can serve for drivers in many sites. The market share of EPB systems is continuously growing from year to year. This figure shows how the fitment rate is position rate of the EPB develops compared to the conventional options. The production of the 60 million EPB calipers in 2015 was a remarkable milestone, and the market share will most likely reach 30% within the next years. The forecast shows that the fitment rate could nearly reach half of the market within a decade. This one. Now back to our test machines. The system architecture of the set of upgraded test machines is described in this figure. This client-server architecture can be recognized in the case of the 3-layer web server architecture. In detail, this is one upgraded test machines. This is fatigue test machine. This one. This is special interface prescaler, and another special interface digital control IP module. You can see also industrial plan, local area network. This is all Linux-based application server and web server and MySQL server. On the next picture, we will deal with this part of for system. Here is detail. You can see here a electromechanical counter in old test machines. This one, totalizing counter, is also the name of this part. The head of IP electronic modules is a frequency divider built around Atmel AT-TINI, this one. The module TCV 112, this module is produced by one Bulgaria firm named Teracom, this one. From Russia. Input signals from electromechanical counters, this one. With amplitude 24 volts are optically isolated. Oh, I lost my laser pen, this one, optically. To ensure a fault tolerance, module of frequency divider is powered from IP module. This frequency module divides the frequency of the input pulses generated by input mechanical cycles in the ratio 1 to 100. The output of the frequency divider ensures an input signal for digital input of the module TCV, this one. And the module TCV, this one, creates one SNMP event. It means Simple Network Management Protocol trap. This is a special internet standard protocol for collecting and organizing information about managed devices on IP networks and for modifying that information to change device behavior. Typically, device support SNMP includes cable modems, routers, switches, servers, workstation, printers, and more. This is very, very old internet protocol like HTTP or FTP. Yes, but at the end, you can see that one SNMP trap represents 100 machine cycles. On the next picture, you can see a wall-mounted panel with 8 electronic counters, IP modules, constructions view. This is this box represents 4 old test machines with cable concentrator and also cable deconcentrator here, and 8 IP modules based on Teracom TCM module. These wall-mounted panels was prepared for presentation purposes for project stakeholders in the plant testing room. And you can see also, sorry for delay, my computer has some problem. Oh, it crashed. My Microsoft Power crashed. Yes, this is a photograph of wall-mounted panel with 8 electronic quantum IP modules. This is actual photo. We connected all developed 8 electronic interfaces with Linux application server and MySQL database server. Users, such test managers or test engineers, access the database MySQL database from a Microsoft Excel database client based on MySQL ODBC database interface. Therefore, we decided to develop a database client program based on Visual Basic for Application, VBA, on the Excel Ring platform. As you can see, the users can see the current status of individual test machines. Current status. LP is derived from word level pulsator, another name term for test machines. You can see that working or not working, so like semaphore lights. To use an Excel and VBA, Visual Basic Application platform on client user side was ordered by Department of Management of Information System in the concrete plan. The strictly policy of the production plan only Excel VBA macros rule is allowed in the test laboratory. Not possible another program. Only Excel platform. Also, this is, you can see another picture prepared by the Visual Basic for application. Within Excel and VBA dashboard visualization of on-day mechanical cycle history and test machine utilization. The user can see from database records the total number of mechanical cycles performed for each component tested based on days or months. Next slide. The user can choose day and month and year, and he can see the results from this database. In this concrete case, LP1, LP3, and LP5, in this concrete day, were done out of the work, didn't work. This table represents 1 month from database, the utilization of test machines. You can see white days. It is not good message for test manager, because test manager is interested in utilization of all test machines. And last slide, a fatigue test of the parts ends by its sudden structural degradation. Therefore, it is not possible to tell in advance when this event occurs. The information system, which was developed by us, will provide the user with information about the end of the fatigue test and record this time. The information system will further provide information on the duration of the break in the operation of the test machine. The break time of the test machine is defined by the end time of the fatigue test and time of starting a new test with another component of the same test machine. This program module was developed also based on Visual Basic for application. Very important remark, all data presented at this slide are not real data, they're non-public matter. It's not possible strictly to show you real data about fatigue test of break. Only data for illustration. Conclusion. At first glance, the modernization of old test machines might seem purely technical problem and does not need to address the broader context of common upgrading test machines. From the point of view of functional safety in the automotion, according to the standard ISO 26262, it was necessary to meet the specific requirements in the modernization of these testing machines. Designs and realized information system as temporary solution was cost-effective solution for 4 years, and it prepared the purchasing a new final testing solution in the production plant. The present modernization solution is also a good example of the cooperation of the university and the production plant. Thank you very much.
Thank you, Juraj. So I'm glad that you have been on time, but we still have some delay. It was applied research from the industrial segment. So once again, I'm familiar. We can discuss internally. If there is one question from auditorium, you can ask. Good. If not, we still have one paper that shall be presented. So Juraj, you was not the last one. So please stay online. And okay, now we will continue with the final paper of this session. It is a nonlinear load characterization using orthogonal apparent power decomposition. And the presenter is Marko Dimitrijevic from Serbia and from Faculty of Electronics Engineering. So hello, Marko. Please start sharing your presentation. And now you are in charge. You can start.
Thank you, Mr. Chairman. My name is Marko Dimitrijevic from Faculty of Electronic Engineering, University of Niš, and I will present our recent work. This is a prototype of an instrument for nonlinear load characterization using orthogonal apparent power decompositions. So what is our motivation to do this work? First, the concept of apparent power decomposition in circuits with nonlinear sinusoidal conditions is very ambiguous notions, and it can be very confusing, probably to students and some novice to electrical engineering. It is also very ambiguous in sinusoidal circuits, but even more complicated in non-sinusoidal conditions when we need to include some harmonics for voltage and current. In non-sinusoidal circuits, we can define reactive and distortion power in different ways, and there is no generally accepted decomposition of apparent power. It's so-called decompositions of apparent power. Also, there is no unique definition of reactive power in such circuits. It was an ongoing debate over 80 years, and still we don't have a unique answer to these questions. There is a lot of papers, a lot of works about power decomposition, reactive power, and so on. But all results are obtained by means of simulations or calculating quantities using some measurements on simple test circuits. Our motivation was to build a prototype of an instrument that can measure reactive power defined with different power decompositions in real time, to build some real-time decomposition instrument. So, to understand power decomposition as itself, we need to review some basic notions. First, most general notion is instantaneous power, that is instantaneous voltage times to instantaneous current in some circuit. And active power, that is related to physical quantity to energy that is dissipated in some circuits as thermal energy or mechanical energy, can be defined as average of instantaneous power. But we also have some other notions as apparent power, that is simply multiplications of RMS values of voltage and current. So the most general decomposition of apparent power is given with these well-known equations, and N stands for some non-active power. This is the most general notions of something that is really not related to any physical quantity in a circuit, but can serve as some explanations in some situations. There is many decompositions of apparent power, let's say some modifications of these previously given equations. And we use some decompositions that are present in the literature. First, the Boolean decompositions, the most common and most well-known. Then IEEE standard decomposition, phase shift method that is used in most devices and power meters today. Then Kimberg's, Sharon's, Price's, Kuster's and Moore's decomposition, Shepard and Zikakani's decompositions, Doppenbrock's and Chernetsky decomposition. I will only mention two decompositions in this presentation for the sake of the time. First, most known and most common decompositions is Boolean decomposition. And Boolean defined the reactive power with these equations as a sum of reactive powers for each harmonic. K is a harmonic order, V and I are RMS values of voltage and current respectively, and phi is some phase for voltage and current. This is the most common decompositions and most used and most mentioned in the literature. The second decomposition I will mention here is a standard decomposition phase, so-called phase shift method for calculation of reactive power, and it is used in instruments, most instruments, and in power meters. It's very simple, and it can be easily reproduced and implemented with Hilbert filter, and it is very cheap to implement such functions, so it is most common in instruments. So we developed the system for real-time power decomposition, which is unique, as I know there is no such attempts to make some instrument to measure simultaneously more than one power decomposition. It has real-time capabilities for measuring and calculating various power components, and whole system is based on the virtual instrumentation principle. So in this picture you can see some subsystems of this unique system. First we have acquisition subsystem based on National Instruments acquisition models. Then controller that has two stages. First stage is FPGA stage, which is in charge for data acquisition and conditioning of the signals. And the second stage is real-time controller or real-time operating system, which hosts the applications that calculates all parameters, all the compositions, find reactive, active power, and some more exotic definitions of power. All measurements and all parameters can be stored on local storage or transferred via TCP/IP network to PC. PC is the third component. It is only front end and hosts front end application for controlling the whole system to give some parameters to control the process of data saving and so on. In this picture, you can see one part of FPGA applications. This is the code that is executed on the FPGA for data collection, multiplexing, and data transfer to the next level RTOS operating system. This is the part of the front-end application. You can see some parameters that are grouped with the composition. Also, user can choose the highest harmonic taken in calculations, can choose one or all three lines in a three-phase system, three-line systems. Also, he can control some parameters of acquisition and calculations, manipulate with data, save data, and so on. I will show the part of our results because there are many tables included in the final paper, so you can see more details. Here we made some demo with 20 different nonlinear loads. There are mainly loads with the constant power consumption. This is CFL and LED lamps. And this is one part of the measurements showing standard reactive power defined and calculated with time shift method. Then Fry's reactive power or non-active power. This is the power of the first harmonic, and this is the repeated measurement for the second array of loads. The more interesting case is a variable load, like personal computer. And in this first picture, you can see the steady increase of active power and apparent power, of course, as CPU utilization of PC are increased. So this is the 10%, 20%, 30%, and so on. Increase of CPU utilization leads to increase of active and apparent power. Reactive power is almost constant for this case. Also, you can see another definition of power. This is reactive power defined with IEEE standard. This is Kimberg reactive power and Budeano's reactive power. They're virtually the same. This picture presents Budeano decomposition. So we have reactive power and distortion power for Budeano decomposition. Those are Kuster's and Moore reactive, inductive and capacitive reactive powers shown in this picture. And finally, in this picture, you can see Sharon apparent power decomposition, two quantities, and Chernetsky apparent power decomposition. It has three components. So those are some results. You also can read the paper. We have in greater detail discuss all the results and give some more explanations. We used all these calculated and measured quantities as signatures for artificial neural network, and we showed that these quantities can be used as specific fingerprints for recognition of some nonlinear loads. This paper is currently in a process of reviewing, so it will be, I hope, published recently. And this is one more application of this instrument. This is instead of these conclusions, we give a prototype of a measurement and data processing system for real-time simultaneous and pound decompositions, and give some results of measurements and application of these instruments. If you have some questions, please don't hesitate to ask.
So, thank you very much for your presentation. So, are there any questions? Probably not. I think that also we have skipped a little bit more than was expected. So it is, it is seen that the topics were interesting. All of the work was, I think, very nice, and we can close this session. So to everybody, it is a pity that we cannot meet personally and discuss after lunch or after coffee, so maybe next year. So I would like to wish you a good time of the day, a nice day, and many success in your future research and works. So bye-bye to everybody.
Okay, thank you.
Bye. Thank you,
Mr. Chairman. See you next time, I hope.
Darius, ciao, ciao.
Ciao.